Hello, welcome to my video series of data structures. This is part 1 of Module 7, the union-find data structure. In this video, we will motivate the development of this data structure. Imagine that you want to build a random maze. We begin with an m by n grid, where each cell represents an individual room in the maze. Initially, the rooms are surrounded by walls, and no two rooms are connected. There are two special rooms in the grid, the entrance and the exit. To ensure the maze is solvable, the entrance must be connected to the exit. This is done by connecting adjacent rooms through breaking the walls between them. For instance, as highlighted by the blue box, breaking the wall between rooms I and J creates a path that connects them. Know that when two rooms are connected, all rooms connected to either of them also become connected. For instance, suppose rooms I1 and I2 are connected to room I, and rooms J1 and J2 are connected to room J. Let Si denote the subset of all rooms connecting to I. In other words, Si contains the elements I1, I2, and I. Similarly, Sj contains the elements J1, J2, and J. In this case, breaking the wall between rooms I and J merges the sets Si and Sj into a single set Sij, which now contains elements I1, I2, I, J1, J2, and J. This means any two rooms within this set are now connected. As more walls are broken, the sets continue to merge until the entrance and the exit are ultimately connected, ensuring a solvable maze. We can summarize our maze construction algorithm as the pseudocode shown here. First, we initialize an m by n grid. We set all rooms to be disconnected at the beginning. Then, we iteratively perform the following steps until the entrance is connected to the exit. We randomly select a wall W. Let I and J denote the two adjacent rooms separated by W. We break the wall W, connecting all rooms that are connected to I with all rooms that are connected to J. In other words, we union the sets Si and Sj. In theory, the rooms in a maze can be represented as equivalent classes. In this context, a subset of connecting rooms forms an equivalent class. An equivalence class is a subset of elements that satisfy an equivalence relation R, which is defined by three properties: reflexivity, symmetry, and transitivity. In our maze example, the equivalence relation R is defined as connects to. Reflexivity means that every element is related to itself. In the maze, each room is inherently connected to itself. Symmetry means that if an element A is related to an element B, then B is also related to A. In our case, if room I connects to room J, then room J also connects to room I. Finally, transitivity means that if an element A is related to B and B is related to C, then A is also related to C. For the maze, if room I connects to room J and room J connects to room K, then room I is also connected to room K. Given the definition of equivalent classes, we can derive an important corollary. Two equivalent classes, Si and Sj, are either identical or disjoint. Let I and j be two elements in Si and Sj, respectively. If I connects to j, or shares any equivalence relation R with j, then all elements that are connected to I are also connected to all elements that are connected to j. In this case, Si and Sj are actually the same subset of elements. Conversely, if I does not connect to j, then none of the elements that are connected to I can connect to any elements that are connected to j. In this scenario, Si and Sj are disjoint. As a result, equivalence classes are also known as disjoint sets. After discussing the essential properties of disjoint sets, let's examine the fundamental operations required by the corresponding data structure. From the pseudocode, we identify two fundamental operations: isConnected and connectSets. The isConnected operation checks whether two elements I and j belong to the same disjoint set. This operation involves two steps. First, find the labels of the disjoint sets containing I and j. Second, compare the labels to determine if they represent the same set. Since the comparison is straightforward, the core operation becomes finding the label of this disjoint set that contains a given element. This operation is known as the find operation. For example, find I should return Si, the disjoint set containing the element I. If find I equals find j, then I and j are in the same disjoint set. The operation connectSets merges two disjoint sets Si and Sj into a single set, which is known as the union operation in general. Because the union and find operations are central to disjoint sets, it is also called the union-find data structure. After understanding the fundamental operations of the union-find data structure, we can now rewrite our maze construction algorithm using these operations. Note that disjoint sets are dynamic. For example, as walls are broken in a maze, the connected rooms also change, requiring efficient union and find operations. In the following videos of this module, we will explore two primary implementations of the union-find data structure. The first implementation is called quick find, which executes the find operation in constant time. The second implementation is called quick union, which executes the union operation in constant time. Thank you for watching, and see you next time.